My name is Gabriel Legorreta Paulin. I'm working for the Institute of Geography at the National Autonomous University of Mexico. My main job here is to elaborate landslide inventory map and modeling landslide susceptibility map. So today I'm going to present a project that is in collaboration with the Washington State Department of Natural Resources, DNR, for modeling landslide volumes. We use a study area in Whatcom County, Washington, United States. So the main goal of this project was to implement two generic landslide volume models that I call the overlay and the interpolation models to estimate sediment production for large landslide inventory maps. Let me give you first a brief overview to put in context these two models and the scope of our work. In general, several GIS applications have been used to map and modeling landslide volumes, heuristically, statistically, or deterministically by using different spatial scales and with multiple scopes. Each one has its own advantages and limitations. But in general, all these approaches and methods can be classified into groups since landslide volume can be considered in two different ways. In the first group, the basal slip plane is used to obtain the total landslide volume. In the second group, the accumulated material or mobilized material is used to obtain the superficial volume. And here also there are several methods, but we use the easy ones. The one is called the overlay and the interpolation methods. The overlay method uses a real pre and post sliding topography to obtain the superficial volume. And if the user don't have a pre-sliding topography, then he can use the interpolation method to obtain the previous topography to the slides. And then he can, by using a real post-sliding topography, he can obtain the distribution of volume over long time periods. In either case, by using the overlay or the interpolation methods, these two methods are prone to some errors that can be attributed to the pixel size, to the shifting between pre and post digital elevation models, or to the interpolation method. Most of the literature showed that the errors go from -10 to 28%. But in the worst case scenarios, especially when you have a shifting between pre and post surface, or when the user uses a third, fourth, or fifth order surface to obtain the slip plane, then the error can go above 700%. Also, the potential error on calculating the volume introduced by the difference between a real pre-sliding surface and an interpolated pre-sliding surface has been poorly studied. On the left side, we have the representation of a real topography. In black line is a cross-section. In the middle, we have the theoretical surface with an interpolated surface. So as you can see in orange, the theoretical surface go above and below of my real topography. That will introduce that the model tend to over or under predict volumes. How much error we can get is part of my results. So in order to address the above problems, we implement the overlay and the interpolation method in our map by using Python. We put it as a tools in our map. And then we tested the two models in a real and theoretical conditions in Sonoma Mountains at Whatcom County in Washington State. In this area, we have 19 deep-seated landslides, but we use only 8 that were mapped with moderate and high confidence. The two models can be used for shallow landslides, or can be used for deep-seated landslide, or can be used only for a single landslide polygon, or for the entire landslide inventory map. So the result of this project is split in 3 sections. In the first section, we estimate the landslide volume by using the overlay method and by using the 2017 and 2006 LiDAR image. In the second section, we address the potential landslide distribution over long time periods by using the 2006 LiDAR and an interpolated digital elevation model. And in the third section, we address the potential volume changes introduced by altimetric variations. To do that, we use the previous interpolate surface and the volume obtained with the 2006 LiDAR as a reference to be compared with other altimetric digital elevation models that have variation between 0 and about 2.5 meters. These other surfaces were created by a filtering process. So let's look at the first results for the overlay methods. The results show that the overlay method is able not only to calculate the volume correctly, but allow to the user to highlight the dynamic of the landslide volume. That will be helpful for classification purpose. So let's see this with the resulting maps and the tables. So on the left side, we have the 2006 and 2017 LiDAR image that are the input for the model. The model will subtract these 2 images to obtain an altimetric changes, and then it will multiply by the pixel size to obtain the volume map. And here, in the scale, you will have positive values. Positive values will represent the loss of material, and negative values will represent accumulation of material. For most of the landslide, the accumulation of material is at the top, and the loss of material is in the central part of my deposit. Now, let's look at the table that is produced by the model. On the left side, we have the landslide geometry for my 8 deep-seated landslide, and they came in a wide range of length, width, and depth. Then the model will produce 12 columns with the information of area and the volume for the headscarp and deposit, and individually for the headscarp and deposit. Also, they will produce the positive and negative values for each part of this. But let's focus on the total volume for headscarp and deposits in the column that is called volume HD. So in this column, we can observe that 6 out of my 8 deep-seated landslide have positive values. That means that during this 11 period of study, they have been active. But 2 of them, landslide 8325 and landslide 9229. These 2 landslides have negative values, and for that, these 2 landslides can be considered as not active or in the future as relic landslide, especially landslide 9229, because these have negative values, accumulation in the headscarp and accumulation in the deposit. In the case of landslide 8325, they have accumulation in the headscarp, but the deposit is still active. Another result of using the overlay method is that the user can obtain the total annual load discharged from landslide. So let's see an example of this by using the landslide 8314. This is a landslide that is called Sweet Creek landslide. It's the largest landslide in my area. It has 1.2 square kilometers, and it has a volume about 448,000 cubic meters. If we divide this sum up of volume between my time period of study, 11 years, Sweet Creek landslide is able to produce 4.1 times 10 to the 4 cubic meters per year. And if we know the soil density of this area, it will produce 9.2 times 10 to the 4 tons per year. How accurate is this value? I will say it's pretty accurate and is in the same order of magnitude as the one that was calculated in 2000 by Whatcom County Public Works. Now let's look the results for the second model, the interpolation method. The interpolation method will allow to the user to fill out the amphitheater shape depression of landslides, and that make a simplification of the landform. With that, we can compare with the LiDAR 2006 and obtain the altimetric changes, and then by multiply by the pixel size, we obtain the volume. In this case, let's use again the Sweet Creek landslide. By using this method, the total displacement surface volume is 2.6 times to the 7 cubic meters. How accurate is this value? I will say it's a very good guess and is in the same order of magnitude as the one that was calculated in 1976 by a geotechnical company and by Mackenzie Johnson in 2002. And finally, let's look at the third result, the potential volume error introduced by altimetric variation. So as I mentioned before, we use the volume obtained with the interpolated pre-sliding digital elevation model and the 2006 LiDAR to obtain a volume. And then this volume is compared with the volume obtained with other altimetric surfaces that were calculated by a filtering process. In order to have a altimetric variation between 0 and about 2.5 meters. So let's look how the filtering process works over my interpolated pre-sliding surface. So we have first the post-sliding cross-section. Then we have in black line, we have my interpolated pre-sliding surface, which is my reference. And this surface is going to be filtered by using a low-pass filter. So we filter 5 times, 20 times, 35 times, 50 times, and 100 times. So as you can see, the effect of filtering make that the digital elevation model in the landslide area lose material at the headscarp and accumulate at the deposit. Now, how we relate these altimetric changes with the volumetric changes? To do that, we use the following table. So on the left side, we have the reference volume obtained with the 2006 LiDAR and the interpolated digital elevation model. And then we obtain the volume for filter 5, 20, 35, 50, and 100, and the percentage of variation of this volume. So for instance, for filter 5, the variation goes from 0 to about 6%. Now, let's relate it the elevation. So we use as a reference the interpolation digital elevation model as a reference. And now we use a technique that is called root mean square error. That this kind of error, we can thought as a kind of a normalized distance between my reference altimetry, which is the interpolated digital elevation model, and my prognostic digital elevation model for filter 5, for filter 20. So the difference between my reference and my predicted elevation for filter 5 is 0.24 meters. And the difference between my reference and the digital elevation model with filter 100 is 2.35 meters. So by using the root mean square error, now we can say that to the sub-meter level, the percentage of variation is going to be between 0 and about 17%. And above the meter, the error can reach above 170%. So that is the result of my project. Thank you very much. And if you have questions, I'm able to answer.